Today we are going to be talking about kinetic energy and the math associated with kinetic energy. So what's going to happen is we are going to move, let's see, what happened here? So we're going to move to the next slide. What is going on here? Oh, that's interesting. Okay, all right. So, do you remember this?
No.
A little bit?
Yeah.
Okay, so here we go. Just to review, that the first law of thermodynamics says what? Do you remember?
Everything is energy.
Kind of. Energy
is present at all times.
cannot, there we go, be created or destroyed. It can be transformed or changed into a different type. Could we stop? Now, you've seen these bar charts before, and it's been a while since we looked at them. But at position A, and maybe this might be helpful if I draw the bottom here. So at position A, does the cart have any velocity? Is it moving at all? No, but it does have height, correct? Okay. At position B, does the cart have any velocity at all? Yes, but does it have height? No, it's at the bottom of the ramp. So when I go to draw the bar chart here, what would I put for position A? It would just be gravitational energy. You might want to. Go ahead. And at position B, what will we say for potential, or what will we say for the energy that's present? It would have what type of energy? Kinetic energy, okay? So now, if I were to write my energy equation, I would have EG equals EK. So that's a review of things that we've done so far. Any questions about that? Now, so now, how the heck do I move forward now? Why is this being... All right, so one of the energy formulas that you're going to be responsible for understanding is the kinetic energy formula. And the kinetic energy formula looks something like this. Huh, what? Yeah, this. So we have EK equals mass. Nope, I lied, not mass. Equals 1/2 m and v squared, okay? Where EK is equal to kinetic energy, which has a unit of the joule. Well, no, wait, why is... The joule is a unit of energy, okay? And as a result of it being a unit of energy, it allows us to keep track of energy in a system. In America, for a unit of energy, we use something called the calorie, okay? So when you eat something, the back of the back of the label will say something to the effect of like 140 calories, right? Those 140 calories are the amount of energy that that particular food has that your body converts into energy, okay? And in other parts of the world, they don't use calorie, they use the word joule. Okay? Now, M would be mass, which would be in kilograms, which has a unit of kg. And at some point, you might be asked to convert grams to kilograms. So it would be grams, 1,000 grams is equal to 1 kilogram, and you might have to remember how to do that. Okay? The other unit that's going to be something that's going to be important here is V, which is velocity, which is going to be in meters per second. Or meters over seconds, okay? Now, there is one other way to write this kinetic energy formula that might be easier, where it would be like EK is equal to 0.5 times M times V squared. 1/2 and 0.5 are the same thing. I'm going to use 0.5 because I know that most of us, me included, are afraid of fractions. So we're just going to use the decimal form. All right? So any questions about that? Can I go forward? So in my first example, okay, I know that this is a kinetic energy problem. So I have EK, I have M, and I have V. And so when I read the problem says a 1,200 kilogram car is traveling at 35 meters per second. How much kinetic energy does it have? So I'm solving for kinetic energy in this problem. I'm told that my mass is 1,200 kilograms, and I'm told that my velocity is 35 meters per second. So in this problem, I'm going to go ahead and just substitute everything into my formula. So I'm going to plug everything in. So it's going to be 0.5 times 1,200 kilograms times 35 meters per second squared. Now, because it's squared, I'm going to take care of the exponent first. So I'm going to take EK times 0.5 times 1,200 kilograms times 35, which is 35 squared, is 1,225 meters per second. So now when I plug this in to the calculator, 0.5 times 1,200 times 1,225, I get a value for my kinetic energy to be 735,000 joules. Okay, so that's a lot of energy. Now, moving on. Another example would be a 500 gram basketball is shot with a velocity of 10 meters per second. How much kinetic energy does it have? So I know that it's a kinetic energy problem, and I have to deal with a mass, and I have to deal with a velocity. So in this case, I have 500 grams, because that's what the problem tells me, and the basketball is traveling at a velocity of 10 meters per second. And then it tells me that it's asking me how much kinetic energy does the basketball have. So in this case, Yes, sir.
Would we need to make the mass 0.5 grams?
Oh, that was gonna be my next question. My next question was, can I use these numbers the way that I've been given them? And your answer would be what, sir? No, we have to change them to kilograms. So I'm gonna change this to kilograms by taking 1 kilogram over 1,000 grams, and that gives me 0.500 kilograms. Okay? So now I'm gonna substitute in, so EK will equal 0.5 times 0.500 kilograms times 10 meters per second squared. So again, I'm gonna go ahead and I'm going to substitute this to be, I'm gonna take care of my exponents. So EK will equal 0.5 times 0.5 kilograms, and 10 times 10, or 10 squared, would be 100 meters per second. So when I solve this, it's 0.5 times 0.5 times 100, I get a value of 25 joules. So hopefully that would make some sense, that a car would have more kinetic energy than a basketball, because a car has more mass. It's also traveling faster. Does that make sense? Okay. There's another formula that you're going to be responsible for understanding, and that's the gravitational potential energy formula, and that looks something like this. Eg is equal to m times g times h. Okay? Where Eg is the gravitational potential energy. Its unit is the joule. Okay? Now, M will once again be mass, and that needs to be in kilograms. Now, G is the acceleration of an object due to gravity. It has a unit of meters per second squared, which would look like this. And H would be height, which would be in meters, which would be m. Now, I need to go back to acceleration due to gravity. So if I take this pen right here, okay, and I drop it to the table, we know that it falls, and we would say that it falls because of gravity. Because of gravity, okay? So on the planet Earth, anytime that we drop something, it goes back towards Earth because of gravity. The force of gravity is acting on that object, okay? But in space, like at the International Space Station, if I took this pen and dropped it, it would just float there. Does that make sense? Because there is no gravity. So when we drop an object, and we drop it and it accelerates toward the ground, if I drop it from here versus here, which is right above the table, where is it going to be traveling the fastest? When I let go of it, or right before it hits the table? Right before it hits the table is going to be traveling the fastest. So what that tells us is that as objects drop towards Earth, they get faster. And if they get faster, they all tend to accelerate at the same rate. And what I mean by that is that if I were to drop this pen in a perfect situation, and I were to drop it and allow it to go for 1 second in a perfect Earth situation, it would travel 9.8 meters. That's what that means. So the acceleration due to gravity always has the same number, which is gonna be 9.8 meters per second squared. This number you're going to have to remember and use. Questions about that?
And that's always gonna be a number.
Acceleration due to gravity will always be that number. Okay? Can I move forward? So, I want to use these new formulas in a practice problem. Okay? So, in this particular problem, I know that it's gravitational potential energy practice, so it's going to be EG, we are going to have a mass, we are going to have gravity, and we are going to have a height, okay? Now, this problem asks me to solve for how much gravitational potential energy does the marble have, so I'm going to be solving for that. The problem tells me that I have 25-gram marble, and the ball is sitting on a ramp that's 20 centimeters high. And because gravity is present, that value is going to always be 9.8 meters per second squared. Do I have to keep my units the way that they are, or do I have to change anything here? What do I have to change? I have to change mass to kilograms. So in that case, I would get 0.0250, I'll do 0 kilograms. And do I have to change anything else? Yes, sir?
You have to change the height.
I have to change the height to meters. So I know that 1 meter is equal to 100 centimeters, so that gives me 0.20 meters, okay? So I have to make sure that everything is in the correct unit. So now I'm gonna go ahead and substitute these things into my problem. So EG is equal to 0.025 kilograms times 9.8 meters per second squared times 0.20 meters. So when I plug this into my calculator, 0.025 times 9.8 times 0.2, I get a value for the gravitational potential energy of 0.049 joules. Yes, sir.
How does the square come into play with
The issue is that the unit is actually meters per second squared, but it's not actually squaring the number. So another way to look at that, and this is one of the ways that one of my old professors used to say it, is he never said meters per second squared, he said meters per second, okay? So that helped him, or at least me, to understand that I didn't do any math of that unit, I just took the 9.8, okay? All right, so, can I go forward? Still writing? Okay. So in this problem, we have a 5-kilogram book that has 750 joules of gravitational potential energy. What is the height of the book off the ground when this system starts? So here I know that because I'm telling you it's a gravitational potential energy problem, so I know I'm going to need to deal with mass, and I'm going to need to deal with gravity, and I'm going to need to deal with height. Okay? So in this case, the problem tells me that the gravitational potential energy is 750 joules. So I already know that. The mass of the book is 5 kilograms, and it happens to be in a unit that I don't have to change. And the problem is asking me to find the height, so I'm looking for height. Now, because gravity is part of this, I have 9.8 meters per second, if that helps, okay? And so now what I'm gonna do is I'm going to go back into my formula and plug in what I know. So in this case, I have 750 joules, which is gonna be equal to the mass of 5 kilograms, times the gravity, 9.8 meters per second, times the height, which in this case is what we're trying to find. So I'm gonna simplify what I can, and I'm gonna take 5 kilograms times 9.8, so that's 750 joules is gonna equal to 49 times H. Now, what do I do to get H by itself? How do I solve for H here? Divide. So I'm gonna take 750 joules divided by 49. So it looks something like this, okay? And when I take 750 divided by 49, I get a value for H to be 15.3 meters. It's pretty tall. Seems like it fell out of a tall building. Okay? Not too bad. But we said, and I'm gonna fill this in, that initially the cart had all the gravitational energy and it had just kinetic energy, and the cart was our system, and we said that gravitational energy equaled kinetic energy, right? Okay, now, so that's getting us back into thinking about this a little bit, okay? So, so if we're looking back at this problem again, okay, and I actually want to do this. So in this problem right here, we have all of the gravitational energy, we have all of the kinetic energy, we know that the cart is the system, and we are given a problem that asks us to calculate how much gravitational potential energy there is. So that tells me that I need to work with EG, with mass, with gravity, and with height, okay? So I'm solving for this value here, okay? I can see that in my problem I have a 100 kilogram mass for the cart, and the cart is at 5 meters. So because gravity is involved, I know that the acceleration due to gravity is 9.8 meters per second. So when I go to plug this into my formula, I know that EG equals M times G times H, right? I know that I'm solving for EG. The mass is 100 kilograms. The gravitational acceleration due to gravity is 9.8 meters per second, and the height is 5 meters, okay? When I plug all of this into my calculator, I get a value for my gravitational potential energy to be 4,900 joules, okay? So if the energy equation that we originally wrote was EG equals EK, right? If I just calculated that the gravitational potential energy is 4,900 joules, what does the value for EK have to be? What does the EK have to be? It has to be the same thing, 4,900 joules. So what this tells us is that at the beginning of the system, here, and at the end of the system, here, the energy is the same. It's just changed from being gravitational potential to to kinetic energy. And so when we keep track of these particular types of problems, that's what we're gonna be trying to keep track of. So your homework tonight is to do worksheet number 7. It is a two-sider. But before I let you go, I want you to note that in the homework, I gave you the formulas at the top of the page. It looked like this. EK equals 0.5 or 1/2. You have the rest of the hour to do homework. Yes.